In this video, I'm going to talk about the first GLM that we are going to discuss is the GLM with the response variable is binary. After talking about the general features of this type of analysis, this is to be followed by the exploratory data analysis, the frequentist model fitting, and the Bayesian model fitting. All codes and data to run this analysis are in the website shown on the screen. This video is part of the book, is associated with the book Statistical Modeling with R that I wrote and published in 2023 and published by Oxford University Press. So many observations and experimental results involve a binary response variable. For instance, when somebody is present or absent, somebody or a species is present or absent, when somebody is ill or not ill, and many other examples. So a binary response variable must be modeled with either a binomial or a Bernoulli probability distribution. Both are the latter is a special case of the former, or the former is a generalization of the latter, as you wish. So the binomial distribution is a generalization of a Bernoulli distribution. The Bernoulli distribution applies to a single realization of a random experiment with a probability of success p. And the Bernoulli distribution is a special case of the binomial when we have a single realization. So either you can view the first as a generalization of the Bernoulli, or the Bernoulli as a special case of the binomial distribution. A key concept that is used when modeling binary data is the odds ratio. The odds ratio is often used in betting as a way of expressing the probability of two mutually excluding events. For instance, they are called as 3 to 1. 3 to 1 means a 3 to 1 ratio, and this 3 to 1 ratio can be expressed as 3 divided by 3 plus 1. The plus 1 is because the denominator is 1, and the denominator is 1 over the same denominator. This is equals to 3/4 to 1/4, and so this 3 to 1 corresponds to a 3 that the probability of p is 3 times larger than the probability of 1 minus p, which is the complement of in a binary random observation. So let's see an example. This is very often used in epidemiology. This is a prospective epidemiological study in which we know whether a baby was either breastfed or bottle fed, and we record whether the adult had respiratory illnesses. So this amounts to a 2x2 table in which we have 952 people divided into groups, the bottle fed and the breastfed, and we have within the breastfed, the amount that were ill and the one that were not ill, and likewise for the bottle fed. This is a very simple 2x2 table. We can compute the odds ratio of being fed if bottle fed. That is, we are in this first row of the table, 77 divided by 458, and the complement is 381 divided by 458. This odds ratio is 0.2. And if a person was breastfed, we are now in the second row of the table, and simply obtain the ratio of decimation of the probability of being ill if breastfed, which is 47 divided by 494, and the complement is 447 divided by 494. This second odds ratio is 0.1. A way of comparing these two odds ratio is to make the ratio of these two odds ratio, and that ratio is 1.92. The interpretation is that it is almost twice as likely to get ill if bottle fed compared to breastfed. So odds ratio is an excellent way of comparing relative risks. So the logit is the logarithm of odds ratio. So the probability of in a random experiment with binary results, this probability is a number between 1 and 0. The odds ratio is a way of transforming these probabilities in a number between 0 and plus infinity, and the logit is a way of transforming the odds ratio into a number that can theoretically range between minus infinity to plus infinity. So the logit is the link function of a GLM with a binary response variable. This arises as a special case of the large table that we saw in the previous video for the general presentation of the GLM. So the logit link function, this shows the logit link function as a probability of success. This is of course is undefined when the probability of success equals 1, because the log of 1 over 0 is undefined, and this is also undefined when the probability equals 0. So this is a sort of this curvilinear shape. This is showing the relationship between pi and the logit is this sigmoid function. For any value of the logit, this inverse logit function transform this estimated logit into a probability, a real number between 0 and 1. So the parameters, as in every GLM, are estimated in the scale of the link function that is inverted. This is inversion in this case, to yield predictions that are comparable to the observed values of the response variable. So there are two main types of binary response variables. First, the group analysis, in which each sampling unit, that is each row of the data frame, has the value as identical values for all explanatory variables. The values are therefore that we are going to enter is the total counts of zeros and the total counts of ones, since all the explanatory variables have the same values for each row. So in R, there's a special format to enter these values. I'm not going to discuss it any further. This comes in a matrix type of format, in which we have the success, that is the event that we are interested in, and the non-success, the complement of the event, as a function of the explanatory variable x. Please see the book for further details in this type of analysis. The second type of analysis, which is by far the most common one, is called the non-group binary analysis, in which the sampling units have different values for at least one explanatory variable. The values of the response variable here are recorded as binary, either 0 or 1. So we use here the Bernoulli distribution, which, as we know, is a special case of the binomial when k equals 1. So we are modeling it on a k. We are modeling here the effect of the explanatory variables on a case-by-case basis. So this is by far the most common type of analysis. So let's before entering into the analysis, let's show how we are going to interpret the parameters of a binary GLM. Let's assume the following. Let's assume that the probability of success is we are going to measure it. We are going to assess the effect of a numerical explanatory variable x on the probability of success, and we are modeling the probability of success in the space of the logit link function. So we are going to model it as log of p over 1 minus p. This will yield an intercept and a slope for the explanatory variable. After inverting, we obtain it's a very simple mathematical operation that we see that for any value of x and for any value of the parameters, the intercept and the slope, we are going to obtain a real number, a predicted probability, which is a real number between 0 and 1. So we can calculate the derivative of the previous equation, this equation here at the right hand of the slide. So this derivative is as follows. Can be shown is the derivative of a ratio, which can be shown to be what I'm writing here. So we can actually notice that here what I'm highlighting in the screen is actually p, and this is actually 1 minus p. So we see that the derivative, the rate of change of the probability of success for any infinitesimal change of the explanatory variable is a function of p, the probability of success. And this is the sigmoid explanation. This is a sigmoid function that we wrote before. So what we're trying to see is that at what value this a change in the for what values of pi this probability, these changes in probability of success, these changes in the explanatory values yield the largest value. So the maximum value of this expression occurs when pi equals 1/2, which renders that the maximum rate of change of the probability for any infinitesimal change of x equals to the slope divided by 4. So we can see it here at changing 1 unit when the probability of success is around 4 is the largest value, has the largest impact on the probability, whereas a change in 1 unit here when the probability is small has a small effect. Likewise, when the change in 1 unit in x when the probability of success is very large has a very small effect. So we are going to simply see this is a way of depicting the effect, the largest possible effect of changing one value of the numerical explanatory variable x on the probability of success. So the example we are going to solve is one involving Australian frogs. It's what ecologists call a species distribution model, in which we have presence and absence of a frog, an endangered frog in the south east Australia. These are presence or absence, ones and zeros, as a function of altitude, distance to the number of pools, the number of breeding sites, the average range, the average minimum of the temperature in the spring, and the mean of the maximum daily temperature in the spring. So the goal is to determine which variables affect the presence, or rather the probability of the presence of a frog in southwestern Australia. So here we are simply computing the proportions of zeros and ones in our data frame. We have 37% of ones and 62.7% of ones of zeros. So the response variable is binary, and there is only one probability distribution that can model it, and that is the binomial distribution with probability of presence, in this case pi, which is going to be a function of the explanatory variables and the parameters that we are going to estimate. And we are going to fit the statistical model in the logit scale in the logit lim function, which is where we can write a linear equation relating the explanatory variables, each with its partial slope, and the intercept, the effect on those on the logit of pi. This is where the model is linear. So we are going to start by standardizing the explanatory variables in order to compare the effect sizes, the relative effect sizes in the logit scales where parameters are estimated. So we simply select here, we use the command scale, we select the numerical explanatory variables. This renders them to a mean of 0, this renders them to a standard deviation of 1, and this simply adds to this data frame df1s, fs for standardized, the response variable. So now in this data frame dfn1s, we have all the scaled, standardized numerical explanatory variables and our response variable. So are these variables related? So for that we make a plot of the presences, less presence or absence. Let's remember that we record them as ones and zeros. This is plotted with a jitter command so as to visualize the points, and this blue line corresponds to a marginal GLM obtained by the ggplot. This shows that as altitude increases, the probability of presence declines. This shows that the average spring rainfall has essentially no effect on the probability of presence. This shows that the number of pools seems to, as the number of pools increases, the probability of presence seems to increase, although this is probably driven by a single point, so we are not going to pay much of attention to that. And here we see the probability of the distance to potential breeding sites and to the number of sites. So some of these explanatory variables are related to the response variable. So second, we answer the question whether the explanatory variables are strongly correlated. and this is to avoid including this analysis is to avoid including variables that have very strong correlations, that are therefore not only redundant in the explanatory capacity but also potentially involving difficulties in the numerical estimation of the parameter values. So this is a plot of all the explanatory variables one against the other. We see that in the upper triangular part of this matrix, we simply see the correlations between them, and in green and we see the correlations discriminated for the presences and for the absences. So we see that some of these explanatory variables are highly correlated. For instance, altitude and the mean of the maximum daily temperature are very strongly correlated. They are essentially the same variable. Likewise, the average of the minimum temperature in the spring is very strongly and negatively correlated with altitude. It's essentially, therefore, again, the same variable. We should select one of the variables between this minimum or maximum temperature and the altitude, and the average rain is also highly correlated. By highly, we mean a correlation higher than 0.7, as suggested by that paper of Dorman and collaborators in 2012 that was recalled before. So the frequentist model fitting, we are going to include these explanatory variables. Notice that we eliminated the average rainfall, the temperatures, because they are essentially reflected in altitude, and so we simply state that family, the common is GLM, and we state the type of GLM that we are going to define. This by default assumes a logit link function. So here are the parameters, the partial slopes, these are numerical explanatory variables, are the effect of changing one unit, which in this case involves one standard deviation of each explanatory variables on the logit of pi. So what are the standard deviations? The standard deviations of the explanatory variables are the following. So if this means that if we change, or if the average rainfall increases in 12 units, the logit of pi increases by 1.17. This is what it means. This is standard error of the parameters, just like we explained in the previous models of the general linear model. And these p values simply denote whether these slopes, these partial slopes estimated in the link scale, in the logit link scale, are significantly different from zero. We also see that a change in one unit, that is in one standard deviation of altitude, has a much stronger effect on the logit of pi than a change of one standard deviation in the number of pools. Now we can numerically compare these parameters because all variables are scaled to have a mean of 0 and a standard deviation of 1. So the logit here means the logit of pi over 1 minus pi when all the variables are set to 0. All the variables are set to 0 when they attain their average value. So this is the logit here corresponds to the value of the logit of pi. The logit of pi when all the variables are in their average values. So in order to assess the goodness of fit of these models, we again use the package broom to gather the input. We using the command augment. This is just shows us that we have a table, a type of data frame with 212 rows, as many rows as data points we have, and 12 columns. The 12 columns are the set of variables that are gathered. These standard residuals are the deviance residuals. And then we are going to replace this default deviance residual for the Dunn-Smyth residuals, and these Dunn-Smyth residuals are obtained with the command simulate residuals of the package Dharma, in which we simply add the model name, the number of simulations that we want, or that we have an integer response. This will add that uniform random deviate. This uniform random deviate that will allow to have a continuous distribution. And here we simply convert these Dunn-Smyth residuals to a normal distribution, and with this we make the following plot. The following plot shows us the residuals against the fitted values. We simply see no pattern here, as it should be for a good fitting model. Here we see that these transformed Dunn-Smyth residuals have a normal distributions as they should when the model fits well the data. And for the rest of the plots, C, D, E, F, and G essentially show a random scatter without any trend. As for the Cook distances, we see that it is one single point that we should identify and isolate to assess the effect of this point with a potentially very high influence on the parameter values. So the fitted model predicts the probability of presence as a function of the effect of explanatory variables. So here are just the 4 of the 212 values, predicted probabilities for the first 4 points, for which we actually observed either zeros or ones. Actually, they happen to be ones in this case. So depending on how we discretize this predicted probability of presence, we can have a certain amounts of true negatives, false negatives, true positives, and false positives. So if we move this threshold to the left or to the right, we would alter the amounts of true negatives, false negatives, true positives, and false positives. So comparing the observed and the fitted values requires discretizing the latter. This is a plot that shows that how the true absences in dashed lines and the true presences in continuous lines, these probabilities change depending on how we move the threshold from the lowest to the highest possible value. Depending on the discretization threshold used, we would obtain different proportions of the predicted zeros and ones. So one solution to the problem is to use the ROC curve. ROC means receiving operating characteristic, which solves the problem and is actually simpler to show the curve obtained with the package proc. The command is as follows, and we obtain something else called the AUC, area under curve. So let's see the ROC curve and explain it. So here we have plot the probability of true presence and the probability of true absences. Of course, we would like to have the highest possible values, and this jagged line corresponds to each of the possible thresholds that are used. So in this rectangle, please see the cursor of the mouse, this would have an area, a total area of 1. It's a rectangle of each side of length 1. So the area under curve actually summarizes this curve into a single number. So the interpretation of the AUC that summarizes that is the pretension, the percentage of the correctly predicted zeros and ones by the model. So and a further metric of goodness of fit of the model is what is called the McFadden's percentage of deviance explained, which is calculated as the deviance of the current model divided by the null deviance, that is the model without explanatory variables. So this means that the model explains 24.8% of the deviance of the data. So to communicate the results, we can obtain a table with the parameter estimates under 95% confidence intervals that could be better shown into a plot. So this, let's recall that this confidence intervals is a set of parameter values that are compatible with the data. So the average slope of distance can range between, say, minus 2.7 and minus 1.8. So all these set of parameter values are equally compatible with the model and the observed data. We can obtain also the conditional curves with the package ggfx, and this shows a set of curves for all these different explanatory variables, and as an addition we can observe for combinations of distance and a set of values of altitude ranging from -2 standard deviation to +2 standard deviations. So all these curves are obtained by setting to 0, that is, setting to their mean the other non-explanatory variables not actually explicitly indicated here in the terms component of the command. So with this we can obtain the following curves, in which we see the effect of the average rainfall, that as the average rainfall increases significantly, the probability of presence does as well. The negative, we observe the inverse relationship with altitude, and here we see the distance to the near impossible breeding site as for different combinations of altitude. 0 means the average altitude, -2 means 2 standard deviations below the mean of altitude. So the Bayesian model fitting, we start by writing the statistical model, which is the same that we use for the frequentist fitting. And with the command of the get prior of the package BRMS, we indicate which are the explanatory variables, and family equals Bernoulli, which means that we are going to fit a GLM with binary response variables, and these are the priors that need to be defined on the logit scale. The logit scale is a scale of the link function in which the parameters are going to be estimated. So the link function is independent of the machinery that we use to estimate parameters. So we are going to set the priors. I'm going to justify this in a second. For the class B coefficients, that is all these coefficients which are the partial slopes for the numerical explanatory variables, and another prior for the intercept, which is this value. So this simply says that we expect a background for the intercept. We expect a background probability of presence to range between 0.2 and 0.6. 0.2 and 0.6, and from this difference, the maximum and the minimum divided by 4 is one approach coming from meta-analysis. Please see the book for details, that allow us to gauge the standard deviation that we should define for this normal distribution. This is normal distribution, I recall, is for the background probability of presence in the logit scale. So we are not saying that it's a negative probability; it's a negative logit. And regarding the partial slope, the priors that we set, normal distribution of with mean of 0 and standard deviation of 0.5, it means that we expect the average value of the slope to be null, to be of 0, and 95% of the plausible values to be between -1 and +1. So the summary of the fitted model, the command is nearly as just the same as we did before, with 2000 iterations, 1000 of the warm-up. We then use a thinning rate very high. We just set it to 1, and here we find the marginal distributions of the model parameters in the logit scale, where the parameters are estimated, and the metrics of the convergence of the Hamiltonian Markov chain algorithm. They had been all very close to 1, suggests that the model has converged. The three chains have converged to a common posterior distribution for each of the parameters, and the very high numbers of the effective sample sizes says that we have a very large number of statistically independent estimates. The interpretation of the mean of the marginal posterior distribution can be done using the rule that we explained before, in that a change in one standard deviation, 1 unit in the number of pools, has a maximum effect of increasing the probability of presence of 0.49 divided by 4. This is the maximum possible effect of 0.122. Because explanatory variables were all standardized prior to the analysis, the values of the mean of the posterior distributions of the slopes can be directly compared, and in this way we can actually say that changing one standard deviation of altitude has twice the effect of changing one standard deviation, the number of pools, on the effect on the logit of the probability of presence. We can also assess, as usual, the posterior distribution for the three chains, which are very nearly identical. They were obtained by the Hamiltonian Monte Carlo algorithm. We can also see that we have a large number, well, essentially all the parameter estimates for the parameter values of each of the chains were essentially statistically independent. Notice the very small values of the autocorrelation. We didn't show the trace plots, but they are all pretty good. You can believe me on that. And we can assess the goodness of fit of the model to the data by calculating using the Dunn-Smyth residuals that can be obtained from the package Dharma using the posterior predictive distribution. So first we obtain the posterior predictive distribution. We obtain 1000 draws. Therefore we have 1000 an object that has 1000 rows and 212 columns. The residuals, the Dunn-Smyth residuals, are obtained with an interesting command, create Dharma, in which the simulated response is the transpose of this marginal of this posterior predictive distribution, just because it happens to need to be in the other way around. The observed response, which is where the response variable and the data frame where it is, and the predicted the fitted predicted response, for which we use the median of the posterior predictive distribution, the median for each of the 1000 rows. And here we said integer response equals to true, because the posterior predictive distribution, as we saw, has all values that are discrete. So these residuals are converted to a normal distribution only in the case where the model fits well the data, using the command qnorm as before, and we put it on this data frame. And in this data frame we essentially add all what we need for the plots of the residual analysis, and these are the explanatory variables, the predicted values, and a way of obtaining from the loop package the Pareto K indexes that allow us to gauge the influence that each value has on the predicted on the fitted parameters, on the posterior distributions of the model parameters. Sorry. So we can obtain, by the way, the Bayesian R square, which happens to be roughly 21%, with a 95% credible interval between 13.7% and 27.7%. So let's see the plots. Finally, here we see the plot of the residuals against the fitted value. Essentially see no pattern. We see that most of the residuals, most of the Dunn-Smyth residuals, with the exception of a few points in the lower tail, happens to be very close to a normal distribution. And in plots C, D, F, G, and H, we essentially see a random scatter without any trend, which are all good signs of a well-fitting model. Here in the final plot, the plot H, we see the Pareto K values and the ranges, which are very good, smaller than 0.5, good between 0.5 and 0.7, and worrisome and pretty bad between 0.7 and 1, and very bad higher than 1. We see that all the values are in the range of pretty good. So there is no single point that happens to be very influential on the posterior distribution of the model parameters. We can obtain PV checks from the posterior predictive distribution. This is our first application of this very clever idea, for which we are going to create a function that estimates the proportion of presences from a set of zeros and one, presences and absences. So this function called presence takes, this is the way of calculating the proportion of presences from a vector of zeros and ones. So so here's the posterior predictive distribution, whose dimension we saw it before. I'm just showing here the first 6 rows and the first 10 columns, all of which are either ones and zeros. So what we do is that we estimate in these 1000 values, 1000 rows of the posterior predictive distribution, the proportions of, we apply this function, we estimate the proportions of zeros and 1 in each of these potential realizations of the potential values of the response variable yielded by the model, and compare it with the observed values. And we see that the observed values is pretty much in the middle. That is a typical predicted value of the model. So the model can actually predict the actual observed probability of presence as a typical result. We can also obtain, but we are not going to do it here, it requires a little bit or just a little bit of R programming, the AUC values. Please see the book on that. We can obtain these AUC values, a distribution of them, from the posterior predictive distribution. Finally, we obtain the conditional curves, in which the essential command is plot the conditional effects from the package VRMS. Here we simply add the variable, the explanatory variable for which we want the conditional effects, changing the value, the name that we add between quotes for each of the variables, and this we yield the predicted probability distribution for each of these explanatory variables, while setting all other variables to 0, that is to their means, and we obtain this type of predicted curves, in which we essentially see that as altitude increases, probability of presence decline. There is hardly any relationship between the probability of presence and the number of potential breeding sites, and the rest is pretty obvious. I think this is a pretty good way of showing the implied relationships obtained after fitting the Bayesian model. So in this video I have talked about the GLM with a binary response variable, starting with an explanatory data analysis, the frequentist model fitting, including an explanation of the AUC related to the rock curves that allows to gauge the predictability of the model, and the Bayesian fitting. All the codes and the data necessary to run this analysis can be found in the website shown in the screen. So thanks for your attention, and I'll see you soon in another video of this series. Thank you.